So the next section that we're going to talk about is molar mass. You guys will recognize this from lab. We've talked about this a little bit in lab. So a chemical compound really is just a collection of atoms. So for example, methane, each molecule contains 1 carbon and 4 hydrogen atoms. So we can calculate the mass of 1 mole of methane using our atomic masses from our periodic table for each element. So we'll write it out for each step. So the mass of 1 mole of carbon, we talked about this a few minutes ago, is 12.01 grams. And the mass of 1 mole of hydrogen is 1.008 grams, but we have 4 hydrogens in our formula, so we will need to multiply our atomic mass of hydrogen by 4. So that equals 12.01 grams total for carbon, and for hydrogen it equals 4.032 grams. Okay. And then we just add those numbers together. So we need to calculate the atomic masses for each element within our compound and then add them together to get a total molar mass. So our total here is 16.04 with proper sig figs grams. And remember, this is per 1 mole of CH4 or methane. So that is our molar mass of methane. Okay, so now we're going to look at another example. Calcium carbonate is something we talked about a little bit in the last few lecture videos. We really named calcium carbonate. So calcium carbonate is CaCO3. So the first part of this problem wants us to calculate the molar mass, and part B says a certain sample of calcium carbonate contains 4.86 moles. What is the mass of the sample? So now we're going to look at how we can actually use molar mass in addition to just calculating it. So first we'll calculate the molar mass of our calcium carbonate. So calcium carbonate is an ionic compound, so it has 1 calcium ion, so calcium is 2+ in this case, and our carbonate is the CO3, which is 2-. So that's a polyatomic ion. So if you go back to that table in your textbook, you'll see the charge on carbonate listed. So we have 1 calcium in our compound, and the atomic mass of calcium is 40.08 grams. And then we have within our carbonate ion, we have 1 carbon and 3 oxygens. So now we know that our atomic mass of carbon is 12.01 grams times 1. We just have 1 carbon. And then our atomic mass of oxygen is 16.00 grams. And remember, we're just getting these numbers from the periodic table. But we have 3 oxygens in our carbonate, so we need to multiply that number by 3. Okay, so now we're going to go ahead and do our multiplication. So 1 calcium ion is 40.08 grams. 1 carbon, 2.01 grams. And 3 oxygen is 48 grams. Okay. So now we're going to add this all up. So 1 mole of calcium carbonate has a mass of 100.09 grams. Okay. So now we have our molar mass. So now we can answer part B. So this was part A, and now we're going to answer part B. So part B tells us that a sample contains 4.86 moles of calcium carbonate. And now we know that there are 100.09 grams of calcium carbonate for every 1 mole of calcium carbonate. So we can use that as our conversion factor. So look at your units that you start with. So we have moles, so we need to put moles in our denominator in order to cancel. So for every 1 mole of calcium carbonate, the mass is 100.09 grams. So this is going to tell us what our mass is of this 4.86 mole sample. Okay, so if we multiply that out and do our significant figures and round, we get 486 grams of calcium carbonate in that 4.86 molar sample. Right. Another example. So isopentyl acetate is the compound responsible for the scent of bananas. Interestingly, bees release about 1 microgram, which is 1 times 10 to the negative 6 grams of this compound when they sting. The scent of this attracts other bees to join the attack. So that's a little scary, but we're going to do some math with these numbers. So first question is, how many molecules of isopentyl acetate are released in a typical bee sting? And the second part asks, how many atoms of carbon are present in isopentyl acetate, or in that 1 microgram of the compound? So let's write out what we're given. So we're given that a bee sting is 1 microgram, or 1 times 10 to the negative 6 grams of isopentyl acetate. And our formula for isopentyl acetate is C7H14O2. Alright, so the first question asks how many molecules of isopentyl acetate are released in typical bee sting. So here you look at what unit you need your answer in. So in this case we need molecules, so we're going to need to use Avogadro's number. But remember, Avogadro's number is a unit per 1 mole of the substance. So right now all we have is the mass of our substance. So we're going to need to go from grams to moles and then use Avogadro's number to go from moles to molecules. Okay, so this is our plan of attack. So we need to calculate the molar mass of isopentyl acetate. So we look at our formula. We have 7 carbons, so 7 times the atomic mass of carbon is 12.01 grams. We have 14 hydrogens, and this is per 1 mole, remember. Okay, 14 hydrogens times 1.008 grams per mole. And lastly, we have 2 oxygens times 16.00 grams per mole. Okay, so let's do that math. 7 times 12.01 equals 84.07 grams per mole. 14 hydrogens times 1.008 is 14.11 grams per mole, and 16 times 2 is 32.00 grams per mole. So if we add that all up, we get 130.18 proper sig figs. We have 2 decimal places in all of these numbers, so our answer needs 2 decimal places. Grams per 1 mole. Alright, so now we know the mass that we're starting with is the 1 microgram. So our units here are in grams, so we need to use the grams. So 1 times 10 to the negative 6 grams times, there are 130.11 grams. So make sure that your units will cancel. Grams on top, grams on the bottom for every 1 mole. So now our grams cancel. We're left with moles, which is what we need. And when you do that math, you get 8 times 10 to the negative 9th moles of isopentyl acetate. Alright, so now we can use Avogadro's number to get the number of molecules. So in this example, we're just rounding throughout, so keep that in mind. So we have 8 times 10 to the negative 9th moles of isopentyl acetate per 1 bee sting. So for every 1 mole, we have 6.022 times 10 to the 23rd molecules of isopentyl acetate. Okay. So we work that math out, and we get 5 times 10 to the 15th molecules. Alright. Second part of the question asks how many carbon atoms are present in 1 bee sting. So we need to look at our formula. So we see that we have 7 carbon atoms in our molecule. So 7 carbon atoms equals 1 molecule. So we can use that as a conversion factor. So we are starting with how many molecules are released in a typical bee sting. So 5 times 10 to the 15th molecules of isopentyl acetate times, for every 1 molecule of isopentyl acetate, there are 7 carbon atoms. Alright, so we do that math, and we get 4 times 10 to the 16th carbon atoms for each bee sting. Alright, so there are a couple examples for how you would use Avogadro's number and combine it with finding molar mass and moles of a certain mass of a sample.